Hello, good morning, my dear warriors. I hope I'm audible and visible to all of you. Welcome to the NCERT line by line series with your captain Shreyas. And yep, we are on to the chapter number 10 of wave optics, which is a very important chapter. And in this chapter, you study the wave aspect of light. Although in the chapter 8 of electromagnetic waves, you have still seen light as an electromagnetic wave. This chapter deals with a slightly different aspect of light, which is the interference and the Huygens principle and some other phenomena attributed towards interference of light. So let's begin with the class, and this is your captain Shreyas. Make sure you are not just liking the video but also subscribing to the channel, because it matters a lot to me and the entire team, because it shows your immense support and love towards me as well as the team members and the entire channel as well. Thank you so much for liking and subscribing, and I hope you guys are doing great. Hi Disha, Evening Star, Madhumati, hi 𝐂𝐴𝐻, welcome aboard. I hope you guys are all doing great. And my dear warriors, this is the NCERT line decoded series, which will decode all the important NCERT lines for your competitive exam and at the same time help you with your board preparation. So let's get started. And yes, we are doing the in-text questions as well. Now, in the introductory part of the wave optics, it talks about the different theories of light, starting off with almost 400 years back when Newton gave his theory where he believed light was particle, and he said the different colors that we see is because the different sizes of these particles. He called these particles as corpuscles. That's why it is also famously called as the Newton's corpuscular theory. And he also said that because these particles, when they enter into a dense medium, they slow down because they have some size and all of that. So he explained why the speed of light changes when the medium changes. But there was another person called as Huygens back in the 1600s, who was again a famous Dutch physicist, who said no, light is not a particle. And he said that refraction, reflection, these phenomena can't be explained by particle nature of light, rather wave nature of light. And he also showed some experiments and all of that. But Newton, being the more dominant guy, people did not believe whatever Huygens said, and his theory was discarded. Although Huygens' theory was actually very interesting, and that is what we are going to study even after 400 years. Even though there were some flaws in it, it has a very natural flow in it. It gives you a proper feeling of how refraction and reflection might be working, and so many other explanations which occur very naturally. Other people like Foucault, Fresnel, and so many others, Young's, they all went against Newton and said that light is not particle. What you are saying it is a corpuscle is not right, rather it is a wave. All of them kept shouting, but nobody believed them until Maxwell arrived after almost 200-300 years, and he gave the electromagnetic wave theory of light. And that's when people understood, okay, wait, light is actually an electromagnetic wave, and he was able to explain all the other phenomena which light exhibits. So there is a separate dedicated chapter in physics. We know electromagnetic waves. So here are the few things like the corpuscular model of light, okay, which was given by basically Isaac Newton. And he also predicted that it bends towards the normal, then the speed of light will be greater in the second medium, but which was again contradictory. And then came Huygens principle. Huygens principle put forward the wave theory of light, but the wave theory was not accepted because Newton's dominance, and light could travel through vacuum, and it was felt that wave would always require a medium to propagate from one point to other. There were some things over there which we'll be talking in a bit. Huygens theory of light. Finally, it was understood that light is actually an electromagnetic wave. So Maxwell put forward his electromagnetic wave theory, and he developed a set of equations. We have seen that, and that's why we know light is basically an electromagnetic wave. And he was able to calculate the speed and explained very different phenomena regarding light. So that is basically there in the theory part initially in the introduction, but mainly we are going to focus on the Huygens principle. So what exactly is this Huygens principle? What did he assume, and why was it even not considered, and why is it even considered? All these things we are going to see. Hi Thanos, hi Mardi, welcome aboard all the warrior Pandus. Nice to see you all back. Yeah, welcome. Thank you for warming up the chat box early morning. So Huygens said that first of all he defined a wavefront. So he's basically, when you drop a stone, the wave spread, every point on the surface starts oscillating at some instant. If you take a photograph, shows circular rings, clearly all the points on such a circle are oscillating in the same phase because they are in the same distance, such a locus of the point. So let's start defining what is a wavefront. So let's define a wavefront. So they start oscillating in phase. Such a locus of points which oscillate in phase is called as a wavefront. Thus, a wavefront is defined as a surface of constant phase. The speed, the next important point over here, the speed with which the wavefront moves from the source is called as the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront. Okay. Now, if you have a point source emitting waves uniformly in all the directions, then the locus of the points which have the same amplitude and vibrate in the same phase are spheres. Hence, we have something called as a spherical wave. Okay, so here they tell that if you have a point source, then you have basically spherical wave because all the points locus which will oscillate together will be in terms of sphere. So a small portion of that particular sphere can be considered as a plane wave and what we know as a plane wavefront. Let me explain this to you with a simple idea. See what they tell, a wave is nothing but a disturbance which moves in the medium or disturbance which propagates around you. When you talk, there is a disturbance, and that disturbance moves everywhere. So to explain that, imagine there is a drop of water which falls on a pond or a lake. The disturbance will move everywhere, and you can see it from the side view. It's very easily seen. See, this drop of water falls. You can see this disturbance is moving everywhere throughout the pond. Now this is the side view. If I see it from the top, then you will see how the disturbance goes here, everywhere. So the locus of all the points which have the same oscillation is called as a wavefront. So right now, as you can see, this particular thing is a wavefront. The wavefront is growing in size. The direction in which the wavefront goes is called as the ray. And in that same direction, and it's exactly in the same direction that the energy of the wave travels. So the energy of the wave is traveling exactly perpendicular. This is the wavefront, perpendicular to the wavefront. So that is what has been explained in the first few lines over here. The locus of the points which oscillate in the same phase is called as the wavefront. The speed with which they travel is the speed of the wave, and the energy of the wave is always perpendicular to the wavefront. So if this is the wavefront, it is always perpendicular, and the speed with which the wavefront moves is also the speed of the wave. So if sound is there, the speed at which the sound wave travels is also the speed with which the wavefront of the sound travels. You can see this is the speaker. So it is basically vibrating. So it is generating some sound. So the speed with which the wavefront of the sound travels is also basically the speed of the sound wave, which we know is around 340 meters per second. For light, it is around 3 lakh kilometers per second. Okay, so it's a huge difference. Now basically, if you have, just imagine this. If you have a point source, what will happen? It will create a disturbance around it. It will definitely create a disturbance around it. And after some time, the disturbance will reach here like this in all the possible directions, up, down, front, back, left, right, and it will look like a sphere. But that sphere will keep growing in size. And it will look something like this. And these are nothing but spherical wavefronts. This is nothing but your spherical wave front. This is nothing but your spherical wavefront. The direction in which the wavefront moves, like this one, these will be called as the rays of the wave. The rays of the wave, like rays of light, rays of sound. So it is the rays of that particular wave. These rays are always perpendicular, and also notice it's the same direction in which the energy will travel. The energy travels exactly in this particular direction. Also, the speed with which the wavefront moves is basically the speed of the wave. The speed of that particular wave, which we have already seen, is the frequency times the wavelength, which is nothing but frequency times the wavelength. Hi Rajan, hi Charanya, welcome aboard. Now, when you go really far from such spherical wavefronts, just imagine you have gone really far. Okay, just imagine I draw one more spherical wavefront. I go really far from it. Just imagine this, something like this. When you are really far from such a particular wavefront, source. Our source is here, and you are really far away. This particular spherical wavefront, which is there, it loses its curvature. As you can see over here, if you just consider a small part of it, it looks as if it is a plane. So it looks like a planar waves front. It looks like a planar wavefront. And a planar wavefront just probably going like this. You won't see much of a difference between the rays of light, although they are diverging in nature, but it will feel as if the rays are approximately parallel to each other. You will feel as if the rays are parallel to each other. So if you had to see it more clearly in 3 dimension, it will look something maybe like this. So just imagine this particular wavefront. Something like this, and the rays of light are going like this. So these are the rays. Are you able to visualize this? So these are the planar wavefronts. Yes, they look almost parallel to each other when you are really far away from a large spherical or from a source, and the spherical wavefront becomes very large. So the curvature loses out and you feel almost like a plane. Is this absolutely clear? Madhumati, Rajan, Charanya, everyone with me on this? What has been explained in the first few lines of this particular NCERT paragraph? At large distance from the source, the small portion of the sphere can be considered as a plane, which we call as a planar wavefront, which they have shown here. So this is a point source, how it is generating spherical wavefronts, and when you go really far away, it becomes a almost planar wavefront. Okay. Now, once we understand what a wavefront is, then come back to Huygens theory. It allows us to determine the shape of the wavefront at a later time. Thus, Huygens principle is essentially a geometrical construction. And this is very important. So what Huygens idea is basically to allow us to determine the shape of the wavefront after any time. So basically, the principle is nothing but a construction method which gives me the shape of how the wave will look after any time, so that we understand how it will look, where it is, what is the shape, what's the size, and all of that. So what is the theory? According to the theory, each point, according to Huygens theory, according to Huygens principle, each point of the wavefront is a new source which is called as a secondary source or a secondary disturbance, and it creates secondary waves from these points which spread out in all the directions with the speed of the wave. These secondary waves emitting from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at some later time. So if you want to determine the shape of the wavefront, we draw spheres of radius. We draw spheres of radius v tau. This is at time tau, and here v represents the speed of the wave in that particular medium. Then you draw a common tangent to all the spheres. We obtain the new wavefront at time tau. In this particular model, there is a particular catch. I will explain all these things. For now, I am just underlining it. We also have a back wave which is also shown, but Huygens argued that the amplitude of the secondary wavelengths is maximum in the forward direction and zero in the backward direction. By making this random assumption, Huygens could explain the absence of back wave. However, this assumption is not satisfactory, and the absence of back wave is really justified from a more complex model of wave theory. In a similar manner, we can also use to determine the wave for different mediums. Now, what he is trying to say in these lines over here, let me tell you. First of all, Huygens believed that whenever you create a disturbance, then that disturbance is basically called as the source. The disturbance is basically called as the source. Now, when I say disturbance, that means it is nothing but energy. So basically, the energy which is being created, that energy begins to flow, and that energy flows in a medium. Now, he said that light travels in a medium called as ether. The medium of light was called ether, and it basically keeps on propagating till it reaches its destination in all directions, you can say, all directions. So there are rays of light, and then there are wavefronts and all of that. Huygens argued that whenever you are seeing a light bulb, a candle, or some spark, some light coming, it is a disturbance in the medium, and that disturbance has some energy which is now flowing, and it is flowing in a medium called as ether. So he said light needs a medium also. It is there in the introductory part about this. But people went mad over this. They spent hundreds of years, because Huygens said light travels in a medium, but nobody was able to find such a medium. So that is why Huygens' theory was also even discarded for that reason, because he said light needs a medium, but actually we know light can even travel in vacuum. He even argued that okay, even in vacuum there is something called as ether, but no such ether was ever to be found nor discovered. So understand that this is one assumption which he made, but actually it is not true. So as per Huygens, if you see, light is a mechanical wave. As per Huygens, light is a mechanical wave that travels in ether. It is not that organic compound ether which you are thinking about. Please remember, this is not true. It is actually a false thing. It is not actually true, but this was his assumption. Please remember that. Now he says that, one second. Now he says that, okay, fair enough, if this is light is a mechanical wave, let's say there is a source which has created a disturbance, and then because of that there was a wave front which was created. So this was a wave front which was basically created. Now what he says is that each point on this particular wavefront, there are infinite such points, so I'm just showing a few of these points. Each point on this wavefront, it will act like a new source, but this source is not the original source, so I will call it as the secondary source. Each point will act like the secondary source. Now when they act like a secondary source, what they will do is they will generate waves. Because of each of these sources. So each of them will now generate waves like this, secondary waves like this, each of them. So they are generating this called as the secondary waves. These are called as the secondary waves. Now why they are generating secondary waves here, and why not over here, and why not over here, why not in the backward direction? So these would be basically secondary waves in the backward direction, secondary waves in the backward direction. Actually the light, whatever is there, it is traveling like this. Why these waves, these secondary waves in the backward direction are not generated? This was made as an assumption. He just said no, it is not generated. For some reason he just chumma made that assumption. He did not give any very concrete answer for that. He just said that if light is propagating in this direction, so obviously the waves which will be generated secondary will also be generated in that same direction in which it is actually it will be generated in the same direction in which it is actually propagating. It is propagating over here, so it will generate waves only in this particular direction, not in this direction. So that is what has been even mentioned over here, that the back wave is not made, and he made an ad hoc, that means on the spot assumption, but actually there is a very complex reason which we cannot discuss here, because of which the back waves are actually not generated. So there is actually a reason, but Huygens did not know it at that point of time, rather he was not able to think about it, so he chumma made one assumption, okay, but there is actually a complex reason for it, why these waves are not generated. So only the forward waves are generated. Now these secondary waves will interfere with each other, and you will see that the new wave after some time can be found by drawing a common tangent to all of them, drawing basically a common tangent to basically all these waves. So this then becomes the new wave after some time, let's say tau. This is the new wave after some time, let's say tau. Now how do I know this is that same time tau? There is a way in which you can ensure it. See, when you are having this original wavefront, and you are considering these small secondary sources which are derived, these are not the original, these are secondary sources, and then you are drawing these secondary wavefronts, ensure that whatever secondary wavefronts you are drawing, their radius the radius of the secondary waves is basically the speed of light multiplied by the time after which you want to draw it. Speed into time gives me basically the distance. Speed into time basically gives me the distance traveled by the wave in some time. So ensure that all these secondary waves that you are showing, their radius is just velocity of the wave into time, tau. So then I will be sure that this gap between these two wavefronts is exactly speed into time, which is the distance between the two waves, or the distance traveled by the wavefront. Is this clear? I hope this is absolutely understood. Electrostatics and capacitance already taught in the NCERT line by line series. Squeaky Cook. Okay, Namaste Swati. Welcome aboard everyone. Okay. Is this understood? Now, using this theory, you can construct the waves for any particular shape also. Say for example, I have been given a random wavefront like this. This is a wavefront which was given to me. I can find how the wavefront will look like after some time by just considering small secondary sources. These are our secondary sources. Then once I have the secondary sources, I will just show the secondary wavefronts, that's it. These will be the secondary wavefronts whose radius, the radius should be how much? The radius should be basically velocity into the time. Then the last step will be to draw a common tangent to all of them. Just draw a common tangent to all of them. So this is the new wavefront. This is the new wavefront after some time. After that time, which is basically tau. Got it? So even after some more time you want to draw how the new wavefront will look like, no issues. Again you take small secondary sources. Again you show the new secondary wavefronts like this. Again you show the new secondary wavefronts like this. And again you draw the common tangent to all of them. So this is the more newer, I would say, wavefront. So you can keep drawing newer and newer wavefronts and see how the wave propagates with time. Very good. Now, based on this principle, you can explain the concept of refraction and you can also explain the concept of reflection. So for that, what they do is basically they take an incident plane wave and see how it refracts. And then they also take an incident plane wave and make it fall on a reflector and see how it reflects. There was an animation, if I'm not wrong, which I've seen. Just a second. Let me see if I can find it. Okay. Through this is better. See, basically, this is a very good example to see this. Observe this now. Okay. So, light is coming from this torch as a plane wave. It will fall over here. It will refract and it will reflect. See how it looks like when it comes as a wave. See, these are planar waves, plane wavefronts. Can you see each of these lines are plane wavefronts? They are coming over here, they are bending and it is also getting reflected. So this is exactly what we are studying over here. This is exactly what we are going to study and very easily seen over here. Now observe one thing, forget the reflection part. Forget the reflection part for now. Just look at refraction. You take any plane wavefront, the lower part, the upper part, the middle part. As it moves, the first part which interferes or touches the medium is the lower part. The upper part of that wavefront has not yet touched the medium. So as soon as the lower part touches, it becomes slower. It becomes slower. It slows down. And as the wavefront progresses, as you can see, slowly one part starts touching the medium and it slows down. But the wavefront which had touched earlier, the lower part of it, had slowed down long time back. The upper part slows down after some time when that part reaches this particular medium. So you will see that the wave would have bent by some amount. Okay, try to understand again. This wavefront reaches here. This part slows down, so it has lesser speed. This is still continuing with the same speed. When it reaches here, then it slows down. But because this lower part had slowed down earlier, you will see that the wave has bent. It's like throwing a pen like this and it enters a rough surface. So this part, lower part of the pen slows down. This part is still fast, so it turns and then it goes down like this. Are you able to visualize? This was going on a smooth floor. This was going on a smooth floor. Now the moment it enters this medium, this part becomes slower. So you can see the pen turns and then finally it goes down like this. Now, is it understood? Neha, maybe for 2 hours or so, who knows? So exactly that is what has been done over here in this entire derivation. So let me explain this to you in a very simple way. If I show you the NCERT slide, you might not really understand it so well. See, this is the surface interface, okay, and then you have the plane wavefront. Okay, so this is your incident wavefront. This is your incident wavefront. So what happens is the ray of light will come like this. Here also it will come like this. Right now it has reached till here. This is the first part which touches this particular medium. So immediately after that, what will happen? This part will slow down. This part will continue moving with the same speed. It has no obligation as such. This part will continue moving with the same speed. It has no obligation. But here what happens is, this part at this point it will generate a secondary wave. Are you able to visualize it? It will start generating basically a secondary wave, but at a much slower speed. The speed will not be much. It will start generating a secondary wave at a much slower speed. Meanwhile, this wave is still propagating ahead. Okay. Next step, let's see what exactly happens. This wave would have gone even further. You will see probably it would have reached here, maybe something like this. Okay, it has probably reached till here. Meanwhile, this point which just touched the medium over here, it will start generating a secondary wave. This secondary wave which was generated before would have by now grown a little bit in size. The next instant, think about it, the entire incident wavefront would finally reach the medium. In fact, the last part also reaches here. Meanwhile, this point which just touched this medium before would have generated a secondary wave here. This secondary wave would have now grown in size like this. This secondary wave would have grown furthermore like this. And now at this moment it has just started to behave like a secondary source. It will generate secondary waves after this. So as a whole, if you notice what exactly has happened, my dear students, okay, observe this now. This particular primary wave eventually reaches here. Meanwhile, you will see that this point will behave like a secondary source. It starts generating secondary waves like this. Okay, that secondary wave, by the time this guy reaches here, has really grown in size. This, when it reaches here, it would have made a secondary wave, secondary wave, secondary wave, secondary wave, secondary wave, like this. This is how the secondary waves would have been generated over a long period of time by the time this point reaches here. Is this absolutely clear how this happened? Again, look at it. This point generates a secondary wave behaving like a secondary source. Then this point will behave like a secondary wave source generating a secondary wave. This would have grown by that time. This will further grow. This will grow. Now this will generate a secondary wave. Now this will generate. So basically you will see these secondary waves, but they are being propagated at a slower speed. They are being propagated at a slower speed. So if you draw a common tangent to all of them, if you draw basically a common tangent to all of them, if you draw a common tangent to all of them, this is basically my new, I would say, refracted wavefront. This is my new refracted wavefront. And this refracted wavefront will continue propagating like this. It will continue propagating like this in this particular direction. It will continue propagating like this in this particular direction. You can see that. So you can see the light has slightly bent because these wavefronts were slow moving. They were slow moving waves. So you can see the bending action of light, hence the light has just got refracted. Okay, so basically that derivation goes something like this, where you show this. Okay, you can start marking some points, like this point I can call it A, this point I can call it B, this point over here I can call it C, this point over here I can call it D. I can also draw perpendiculars. I can also draw perpendiculars over here like this. That is basically the normals. So I can just show the normals over here like this. And I can start showing the angles of incidence also. This will be the angle of incidence, even this will be the angle of incidence. Then this would be the angle of refraction, even this would be the angle of refraction. So that is how the diagram will look like. Okay, after some time, the incident wavefront has turned into a refracted wavefront and it has turned by some angle. Now, one thing is clear. In the time, let's say tau, the incident wavefront AC's point, this incident wavefront AC's point labeled C reaches B, it reaches, this C reaches B, I would say the secondary wavefront generated at point A reaches, this point A's wavefront would have just reached point labeled D. So by the time this reaches here, this wavefront which was generated before will reach over here. This is seen in the simulation over here. So this is still here. This has now just started behaving like a secondary source. It will generate secondary wave. It will generate, and finally you will see this point has reached here. This has reached over here. That is what I am trying to explain over here. Okay. Now, what you can say is basically this particular distance labeled C to B is nothing but speed of light into the time taken, and similarly the distance A to D is speed of light into the time taken. Time taken is the same from here to here or here, but the speeds are obviously different. Okay, now you look at this triangle and look at this triangle. Well, if this angle is I, or rather this angle is I, guys, think about it. This angle will be 90 minus I, and this angle will be I again. Similarly, over here, if this angle is R, this angle will be 90 minus R, and this angle will be R again. Okay, so now think and tell me what will be sine of angle I. Sine of angle I in this right angle triangle is opposite side, which is nothing but CB, divided by hypotenuse, which is nothing but AB. Similarly, if you just try to find what is sine of R opposite in this triangle, opposite side is nothing but AD upon the hypotenuse which is basically AB. So how about dividing both, because I can see AB is common. So if I write sine of I and divide it with sine of R, clearly what I get is AD over here and I get CB over here. That's it, equal to. Is that right? Because AB and AB will get cancelled. So sine I by sine R will be this by this by this by this. AB and AB obviously has got cancelled. AB and AB has just got cancelled. But wait a minute, what is CB? CB is nothing but V1 tau. What is AD? AD is nothing but V2 tau. Tau also gets cancelled. So what am I getting? What am I exactly getting? Sine of I is equal to sine of I by sine of R is V1 by V2. This particular ratio is nothing but a constant. This is called as the refractive index, and this will be a constant because the speed of lights are the same in a particular medium. So if you take a medium, V1 will always be the same. V2, if you take some other medium, V2 will always remain the same. So this ratio is constant. So that is called refractive index, and this is nothing but your Snell's law. So that is how Snell's law can be proven. That is how Snell's law can be proven. Got it? Tau is nothing but the time. In the time tau, time is taken. I can take T, T1, T0, T0, capital T, tau, whatever, some symbol for time. 5 seconds, 3 seconds, 100 seconds, 1 minute, 2 hours, 0.1 millisecond, anything. Cool. Now the same thing analysis is also done for dense to rare over here. It's instead of bending towards, it will bend away, it will speed up. So you can see it will bend away. That is what has been shown in the next diagram. That is not so important, but you have seen it. Now over here, the next part is about reflections explanation. How you can explain the law of reflection using Huygens principle. Again, they use some geometry and they have explained how this is the law of reflection. Once we have the laws of reflection and refraction, everything else can be understood. We'll come to that. Okay, but before it, let's see how the reflection can be explained in a similar way. It is very simple, not that difficult. Again, you take a mirror. Again, you show this is basically your incident wavefront. These incident wavefronts are propagating slowly. They will keep going like this, they will keep going like this, and they will fall onto this particular mirror. They will fall onto this particular mirror and they will get reflected. So how will that exact reflection occur? Let's have a look. So as time progresses, eventually you will see one side of the wavefront will reach the mirror, which is the reflector. Meanwhile, the other part of that wavefront would not yet have reached the mirror. So it is still in air. Now the point which reaches this particular reflector, which is nothing but a mirror, it will start generating secondary wave. But remember, this time when it behaves like a secondary source, when it behaves like a secondary source, it won't generate a secondary wave here. Because it is a reflector, it will reflect, so it will start generating a secondary wave here, and that too at the same speed. So it will generate a secondary wave exactly at the same speed with which these waves were traveling. Now, okay, fine, it is now going to behave like a secondary source. It has now going to start generating secondary wave. So after some time it generates this secondary wave. Meanwhile, what would have happened, this particular wavefront would have gone little bit ahead over here, and this point will now behave like a secondary source. The light has gone slightly more ahead like this. In the next instant, you will see that same light will go even more ahead, and then this point will behave like the secondary source. Meanwhile, this secondary source would have generated the secondary wave. This secondary wave would have grown in size. After some more time, you will see that maybe eventually this entire incident wave will finally reach over here, and then this will behave like the secondary source. Meanwhile, this would have already generated a secondary wave. This secondary wave would have already grown in size. This secondary wave would have further grown in size. So that is how the secondary waves start getting generated. So in general, if you see what would have happened, in the time this wavefront eventually reaches over here and then behaves like a secondary source, the initial secondary source, which was starting to reflect the light, would have grown much larger in size. The other secondary sources, not so much in size, but will look probably something like this. Will look probably something like this over here. These are the reflected wavefronts. These are the reflected secondary wavefronts. What do you do to such reflected secondary wavefronts? Obviously, you have to draw a common tangent to all of them. You have to draw a common tangent to all of them to figure out the reflected wavefront. So this then becomes your reflected wavefront. Reflected wavefront. And this particular reflected wavefront then obviously will go like this, will go like this. So the incident light was reflected. So the incident light was basically reflected. Got it, my dear warriors? Yep. Yes. Thank you so much, guys, for reminding me to hydrate. So this is how reflection occurs. All right. Now, based on this, you can find out how the wavefronts will look like for any kind of object. Like for example, they have given over here for a prism, for a convex lens, for a concave mirror. So these kind of questions have come in the exams as objective type. How to figure this out is not very difficult. See, whenever light will travel through a medium, it will become slower. So think as if you are taking the wavefront as a pen and the lens, prism, whatever as a rough surface. So imagine this particular pen was traveling, it encounters a rough surface. So the rough part will slow down the pen, and this part is rough but only for smaller duration. This is rough for a longer time. So the pen will slow down over here for a longer time. This will be also slowed down but for not so long. So that's why the pen will bend like this. So think of the wavefront also to be exactly like the pen and the medium to be like a rough patch. Here also, just imagine the rays which will go here, they will be slowed down for a smaller time. Rays which will go here slowed down for a smaller time, but here they will be slowed down for a longer time. So here they are slowed but for less time, so they will come out and go fast. Here they are slowed but less time and they will come out and again go fast. Here, because they are stuck for a longer time, by the time they come out, they are much behind these two people. So that's why you will see the wavefront is bent like this. That's why you will see the wavefront is bent like this. Is this clear? Understood how to solve these kind of questions? Similarly over here, if you have a parallel beam of light which is incident on a concave mirror, just imagine when the light rays will fall over here, this will behave like the secondary source, this will behave like the secondary source, but this will behave like a secondary source later on, because these rays will hit first. Which rays will hit first? The rays on this part and this part. This part will hit first, whereas this ray will hit the mirror after some time because it is much ahead of these 2 points. So they will start generating waves first. This will generate, but after some time. Meanwhile, they would have grown in size. All right, they would have grown in size over here. So if you draw a common tangent, it will look something like this. So that means the rays will finally meet somewhere at the focus. So this plane wavefront has been turned into a curved wavefront. So that's how the wavefront behavior is. Cool, clear, very good, Sukanya. Awesome. Che Sukwasi, you completed 2 chapters of physics. You can't complete, realistically speaking, or the entire physics in 1 month. 12th standard, at least the high weightage, yes, and that is a good plan. Don't try to push yourself just to complete physics, because then you will lose out in chemistry and biology. Keep a realistic plan. By January end or February, you will complete the syllabus. That is also decent enough. Trust me. You will get good time for revision. Because if you just try to cover the syllabus, you will feel exhausted. You will forget everything. You will not have time for revision. You will not do it in depth. You have time, and I have given a plan on how you can complete the syllabus by February, March and still do 2 revisions. Just check out my old video. Okay. So let's have a look at one of the examples when light is incident on a surface which has 2 media. The reflected and the refracted light both have the same frequency. Why? See, it's very simple. Why, when light which is falling on a surface, why when it gets reflected or refracted, the frequency never changes? Because frequency is the rate at which the disturbance occurs. It has got nothing to do with the medium's characteristics, whether it is a reflector, whether it is a lens, whether it is a prism. If the disturbance reaches here, and then after some time the disturbance reaches here, after some time the disturbance reaches here, that defines the frequency of the wave. How frequent are the crests moving? How frequent are the troughs moving? So once I know every 5 seconds a crest is reaching, that's it. After 5 seconds, I know a crest will be generated. Yeah, that crest might move slow, fast, depending on whether the medium is dense or rare. But that cannot be, that cannot deny the fact that the crest will still be generated after every 5 seconds. Just because it is moving slow does not mean the frequency will change. No. The frequency will remain unaffected. Okay, so it's the rate at which the disturbance is being created and how it moves. When light goes from rare to dense, the speed decreases. Does the reduction in speed imply a reduction in the energy carried by the wave? What do you think? Do you think energy also goes away because it has now become slow? Obviously not. Energy can't be destroyed or created. All such questions, wherever energy, is it conserved? Always the answer is yes, energy is conserved. So is energy being lost somewhere and is it disappearing somewhere? Always the answers are no. The energy is not, you can't magically disappear that energy. So it definitely is not going anywhere. In fact, the amplitude of the wave might change to make sure that the energy is still preserved. Yeah, the speed might be slow, but maybe the amplitude becomes large. Maybe then it compensates for it. In the wave nature of light, intensity of the light is determined by the square of the amplitude. What determines the intensity of light in the photon picture of light? Well, if you remember, when you take wave nature, intensity is always proportional to the amplitude square. This is true for a wave. But when you take a photon, remember the intensity, I have just discussed this in yesterday's photon, your day before yesterday's photon photoelectric effect class. There is a formula given by N by T HF by A. It depends on the number of photons which are incident per unit time and not on the amplitude. Because how many photons of light are going decides how intense that beam of light is in the particle nature of light. Yep, very good. Cool, great. So now let's discuss something called as coherent and incoherent sources, and then let's come to the main part, which is the interference of light and Young's double slit experiment. Now what is this coherent and incoherent? You might have been in an assembly prayer or maybe some class songs have to be sung, you have to sing in a chorus or you are in a part of a group song or something like that. 100% you would have played some kind of role in your school or in your college. Have you? Are you good at singing in chorus or in a group? Maybe not one or two people, maybe at least some 5-10 people, or the entire class has to sing some prayer or something. Imagine that prayer has some nice notes or it has some crazy, I would say tunes. One person is singing in one way. One person is singing ah, one person is singing ba, one person is singing ma. So it will not sound very right. But if they are in sync, it sounds so melodious or it sounds better. So coherence means you are in sync and you are having a kind of relationship. And it is not necessary everybody has to say the same thing. Like, okay, when the drummer is hitting a beat, then this lyrics has to be sung, or maybe the keyboard person has to play a certain tune. It has to be in a rhythm. There has to be a relation. When I'm giving the beats, with the beats, you have to make sure your tempo of the song is, or the pace of the song is, and accordingly you are strumming the guitar or you are playing the keyboard along with the rhythm. So if you are in the rhythm, you are in the sync, such a system of sources, such sources are said to be coherent in nature. Coherence means you are in rhythm, you are in sync, you are maintaining a phase, you are keeping that situation intact. Whatever situation was there before, you are making sure that situation is intact. So whenever the drummer hits, after a second, you are always saying a particular lyric or a tune. Again, when he hits, again you are making that pitch high. Again, when another beat comes, then the tune is something different. So you are maintaining a phase or a situation. Incoherence means you are just random. The drummer is hitting on his own, the keyboard person is doing something on his own. It's looking like one ridiculous performance, as if you are going to get tomatoes thrown on your face. Okay, so everybody is doing their own stuff. The drummer is like, no, I will be very fast. The singer is like, no, I will be very slow. I will sing as if I am very, very sad. The pianist is as if he feels like he's opening the track of some Christopher Nolan movie. The keyboard guy or the guitarist is saying that, no, I feel like I'm in a rock band and he's playing a rock song. So this kind of thing, there is no sync, is called as incoherence. Now, because incoherence means that there is no sync, there is no rhythm, there is no relationship, there is no point discussing such an incoherence behavior because it is random. How do I talk about something which is random in nature? I don't know what they are going to do. So sometimes the light is bright, sometimes the light is faint, sometimes the light is green, sometimes the light is blue. I don't know what they are going to do together. But I know, okay, this is blue light, this is also blue light, this is the amplitude, this is amplitude, okay, they are going to be together here, and every time this is going to happen. Then I can comment, I can formulate, I can discuss about it. So that is the reason why we discuss coherent sources and we do not study incoherent sources. Is this clear, my dear warriors? Yes sir, I sing a prayer. Swati, very good. So I hope you are a coherent singer at the prayer. Because I was an incoherent singer. So I was always that person in the class along with a small group of kids who used to make sure that our class never wins in any kind of singing competitions. We will always make sure that we are out of tune. Yes, it will feel like there are 2-3 donkeys in the class who are trying to make it out of tune. Yep. So the entire field of interference is based on the superposition principle. At a particular point of the medium, the resultant displacement produced by number of waves is the vector displacement of these waves. Consider two needles moving periodically up and down, they produce water waves, okay. Then, okay, over here they talk about coherence. The phase difference between them, if it is not changing, then they are said to be coherent in nature. That figure shows coherent sources, and then they basically do some kind of derivation. Examples of coherent. Which are coherent? Example, this one. Yes, these both waves are coherent in nature. These both are coherent in nature. Okay, so definitely these two are coherent in nature. Then look at this. Sorry. Even these both are coherent in nature. They are not identical, but they are coherent, meaning, see, this is going up, down, down, up, down, down, up, down, down, up. Yes, they are again coherent in nature. Even this is coherent. Just look at this. Even this is coherent. When this is a trough, this is crest, crest, trough, trough, crest, trough, crest, crest, trough, crest, trough, crest, trough, crest, trough, opposite. So it is maintaining the phase difference. So basically the phase difference is nothing but a constant. All these are coherent. Which are not coherent, let me give you those examples also. This, yes, definitely not coherent. Or something and all, this is, these two have no relation only between them. There is nothing that you can relate. So they are incoherent sources. Okay. Now we are going to study the interference of such coherent waves. So for that, let's come back over here. Remember, a speaker can generate wavefronts. Even, by the way, light can generate wavefronts. So this is the wavefronts of light, beautifully looking. You can see how light is being generated. This was green color light. Now if I use violet color light, see the violet light is looking like this. I don't know whether you can see it. If I use red color light, you can see it like this over here. Look at how red color light, the distance between the wavefronts is slightly larger because light has a larger wavelength. Yep. Whereas if you look at violet color, you can see they are slightly closely spaced because the wavelength of violet is lesser as compared to yellow or basically red. As you can see, yellow is slightly larger, and then when you make it red, it is the largest among the visible spectrum. It is the largest among the visible spectrum. Now I will create two such wavefronts together. Let's create two such wavefronts together, and for that we'll create interference. First, let's study with water, then we can go to sound and even light. It is a general phenomena. This theory is not just limited to light. It is although a part of wave optics. You can use it in sound or even water or anything else. So let's start generating wavefronts over here. You can see drops of water are falling on the pond over here. Wavefronts are being generated. Now if I turn this off, it's gone. Okay. If I turn this on, it will generate its own wavefronts from here. So this is another source. This is the first source. Now what if I turn on both the sources together? Then what do you see? They are in sync, they are synchronous, they are in phase, or basically phase difference is constant, so they are coherent sources, and you can see some kind of interference being happening. The crests are meeting, the troughs are meeting, somewhere there is constructive interference, somewhere there is destructive interference, and so on and so forth. So wherever constructive interference is there, these water drops, those ripples which will be formed, those tides will be high, and wherever there is destructive interference, that means the waves cancel out each other, there will be no variations in the tides. The ripples will cancel out each other. Probably somewhere here you can see there is no variation, only much somewhere here in this line or even in this line there is not much variation, but here I can see a lot of variations. It's going down and up, black is down, blue is up, so a lot of variations are there. We can try it out with waves also for sound. This is a speaker generating a wave. This is another speaker also generating another wave. And we can see how at some places constructive interference is there. That means if you stand over there, both the speakers will have a constructive effect. Means you will hear a loud sound and you will hear a very good intensity of the sound. But there are some places the waves are cancelling out each other. So that sound is getting interfered destructively, means you will not hear any sound. And that is actually very funny to think of. There are two speakers in front of you, yet when you are standing in front of them, you are not able to hear anything. So this is actually a technology which is used in many of the cars, modern cars, like the high-end cars, like Rolls-Royce or maybe the Mercedes Maybach and all of that, where they ensure that if the backseat passenger is talking on a business call to his client or his customer or to his business colleague, the driver won't be able to hear anything, and that is being taken care of by noise cancelling and interference of sound. So they have multiple speakers in the car and they ensure that if the backseat passenger is on the call, maybe he's a very important person, politician, who knows, maybe some military discussion is going on, the driver won't be able to overhear what is happening because he's in the destructive zone of interference. We can separate them out or we can bring them close, and you can see how the interference patterns will change. Look at it. Now they are very, very close. Now the interference pattern is looking way, way different. I can see these lines, okay, making some angle. If I change this, you can see it is way, way different now. Observe how things change drastically. Okay, so the interference patterns change as you change the distance between the sources, and not just that, it also depends on the frequency. If I increase the frequency also, you can see how the interference patterns will change. Yes, the interference pattern has changed. I have increased the frequency. If I reduce the frequency, again the interference pattern which is obtained will again change, obviously. We can also see it with particles, how the particles behave. This is the particles of air, how sound travels in reality. So you can see there are some particles which are actually moving back and forth a lot, but you can see this zone or even this zone over here, the particles are not moving much, so very less sound is there, whereas at some places the sound is really, really high. Same thing applicable even for light. So let's say we use both these lights, and both these light sources are switched on together, they are coherent necessarily, then you can see some places there will be a lot of brightness, some places there will be absolute darkness. Yes, some places it will be bright, some places it will be absolutely dark because of destructive interference. I can change the separation. Again, I will see the interference patterns will change, as you can notice. I can also change the wavelength or the frequency of the light. Automatically, again, the nature of the interference will definitely change. The best part is you can observe this interference on a screen through a naked eye by placing a screen in the front. Wherever constructive interference is happening, you will see bright regions over there. These are bright fringes, bright bands. And wherever destructive interference is happening, you will see dark fringes over here. They are the dark bands or the dark fringes. And you can see changing the separation obviously changes the manner in which the bright and the dark fringes are created, how far they are separated. Now you can see one big bright fringe, so the other bright fringe is way out of the screen. Maybe I'll have to change the distance between the sources. Maybe then I will be able to see it. Yeah, so how much fringes you can see, what's the width, what's the distance between them, all that depends on the distance between the sources and even the light's frequency or the wavelength, as you can see over here. See, I've changed the wavelength, I've changed it to blue color now. You can see now the fringes are very, very different in nature. The fringes widths are different, the distance between the fringes are also different. You can see the intensity graph over here. This is minimal intensity, that means it's a dark fringe. Maximum intensity means it's a bright fringe. Dark, bright, dark, bright. You can see it for different colors also. Let's say yellow color also, we can try it out. I can choose some different separation. Observe this, how it behaves. There is a screen which is placed in front. You can see the plot, the intensity over here. Dark, bright, dark, low intensity, bright, high intensity. Dark, low intensity, bright is high intensity. So this is how the intensity graph will look like. Now basically this setup what you are seeing with light is called as a Young's double slit apparatus or Young's double slit experiment, where they use two slits and there is a light source. The light falling from that source enters through these two slits, and these two slits behave like two coherent sources, and their light eventually through a dark room falls on a screen and you see a pattern which is a fringe pattern, bright and a dark fringe pattern, alternate bright and dark bands. From this you can do calculations of whatever you want, either the wavelength, the distance, whatever you want. And this experimental setup is called as a Young's double slit experimental setup, YDSE. So after the name of the scientist, physicist Young, there are two slits. Instead of two light sources, there are two slits which are made, small holes. There is a bulb here. The light falls on this, but only a small part enters from here and here, and that light finally reaches the screen after interference, producing this fringe pattern. Are you able to visualize this? Yes or no? Are you able to understand whatever I explained till now? Let me know quickly in the chat box. Did you understand what interference is? What is a dark fringe? What is bright fringe? Yeah, we'll do the calculation part now. Hold on. But did you understand all these things is the main question. Yes, everyone? How this works? If you just turn on one, then there is no interference pattern at all. Look at this. I've turned this off. Only one light source is there. Then you will see the entire screen will get illuminated. There is no more interference. No more interference. Very good, Sukanya. Evening start. Awesomeness. Very good, Madhumati. Crystal clear. Mardai. Very good. Awesome. Okay. So here, where did they go? Yeah. After this, they have done some derivations over here. All right. And then they have given some formulas over here and then over here. So we'll see what these formulas and these derivations are in a very simple manner. First of all, when you talk about constructive interference, although we have discussed this for waves and superposition, I'm just repeating this aspect again over here. If you have a wave like this, in such a case, if you add them together, by the way, here delta x, the path difference is 0, the phase difference is also 0, or let's say like this, this is exactly having a path difference of lambda, which means the phase difference is 2 pi, and you add both these waves, or this path difference is 2 lambda, the phase difference is 4 pi radian. All these cases, observe carefully, the trough meets the trough, the crest meets the crest, the crest meets the crest, the trough meets the trough, the trough meets the trough, the crest will meet the crest. All these are examples of constructive interference. Path difference can be 0, lambda, 2 lambda, in fact even 3 lambda. All of them will give a big amplitude. It will give them a big amplitude, yes, of interference. It will give a big amplitude, and in general I can then say that my path difference can be n times of lambda, my phase difference can be even multiples of pi, meaning over here this can be lambda, 2 lambda, 3 lambda, and so on and so forth. This can be 0, this can be 2 pi, this can be 4 pi, 6 pi, like that. And the net amplitude in such cases, is just the first amplitude plus the next amplitude. Whereas if you talk about the intensity, that will be also maximum, and we have derived this we have seen this in this particular lecture. If you have missed this class, I'll just show it to you over here. Superposition of waves, where did it go? Interference, standing waves and beats. Just check out this lecture. You will find that theory where I have discussed about interference. Okay, right over here. You will see in the beginning, yes, in phase, out of phase. We have seen it graphically. I have shown you how it works. All these things has been discussed right over here. So just check that out. So the intensity is maximum, and it will be root of the first wave's intensity plus root of the second wave's intensity whole square. Yeah, that is what the intensity is going to be. And constructive interference happens when the waves are basically in phase. They are said to be in the phase. That's when you will get, yeah, maximum intensity, constructive interference, maximum amplitude. This amplitude is not just any amplitude. This is the maximum amplitude that you can get of that waves which are interfering. Are you reminded of it, everyone? We'll not be doing modern physics NCERT line by line because like I said, modern physics is better learnt through normal NEET theory, not through NCERT line by line. So it's better to do it that way. And already in NEET Express Station 0, it was done in that particular way. Now, similarly, when you talk about destructive interference, when you talk about destructive interference. That means the waves will be out of phase, out of phase. So things like this will happen. These two are added. Over here, you can see the path difference is lambda by 2. Basically, the phase difference is pi radian, or yeah. So you can see this is 3 lambda by 2, and here the phase difference, if you do the calculation, it will be 3 pi radian, so on and so forth. You can add these two waves. What you will see is a smaller wave. You will see a smaller wave because it is destructively being interfered. Okay, so in such a case, the phase differences allowed and the path differences will be, the path difference can be lambda by 2, 3 lambda by 2, basically it is odd times lambda by 2. Now lambda by 2 is 0.5, 3 by 2 is 1.5. So it will be basically like 0.5 lambda, 1.5 lambda, 2.5 lambda, so on and so forth. But if it is integral lambda, 1 lambda, 2 lambda, 3 lambda, then it is constructive interference. And you can see over here, the crest meets with the trough meets with the crest. The trough meets with the crest. Okay, the next crest will definitely be meeting the trough over here, like this. So it is definitely a destructive interference. Whereas if you talk about the phase difference which you will get over here, you can see it is pi, 3 pi. Pi is basically out of phase, opposite. So basically odd multiples of pi. So basically it will be nothing but pi, 3 pi, 5 pi, and so on and so forth, 7 pi and all that. The amplitude will be the least that you can get. So whichever is bigger minus whichever is smaller. So mod of A1 minus A2 will be the amplitude. If you ask me the intensity, that intensity will also be minimum. It will be root of I1 minus root of I2 whole square. Root of I1 minus root of I2 the whole square. Is this clear, everyone? Okay, perfect. Now just imagine, say for example, if the two coherent sources causing interference are identical, if they are identical, that means A1 is equal to A2 is equal to A, I1 is equal to I2 is equal to, let's say, I will call it I, then the maximum amplitude that you will get is nothing but A plus A, which is 2A, and the maximum intensity that you will get is root I plus root I whole square, which is 2 root I the whole square, which is basically 4 times of I. This is the maximum that you will get. This is for your constructive or for maxima, or the maxima that you can talk about, where everything is maximum, or where everything is going to be bright and loud. If it is a sound, it will be loud. If it is light, everything is bright. This is what the intensity will be. It will be 4 times of I. The amplitude will be double of the each wave's amplitude. That is for the constructive part. But if you talk about the destructive part, the amplitude will be the least. In fact, it will be A minus A, both are the same, it will be 0. This is called as a perfect destructive interference. It is a perfect destructive interference because it is cancelling out. The intensity will be minimum. In fact, that will be root of I minus root of I, the whole square, it will be 0. It is then perfect destructive, nothing is there. And this is your destructive, or I would then call it as the minima part of it, or this will be the dark region of the interference because of those two sources. This will be the dark region because of these two particular sources. We also know that when this thing will happen, in general, if you want to find the intensity, in general, if you want to find the intensity or the amplitude will be given by root of A1 square, this is the resultant amplitude, A square plus 2AA cos del phi. In general, you can see A can be taken out common and I will be left with 1 plus 1 plus 2 cos del phi. This can be further written down as nothing but I can just take over here root 2 1 plus cos del phi. That is what I can write it down as. If you want, you can write 1 plus cos del phi, 1 plus cos del phi as 2 times cos square delta phi by 2. This is a trigonometric formula. If you know this thing, cos 2 theta is equal to 2 cos square theta minus 1. Take that 1 over here. So cos 2 theta plus 1 is 2 cos square theta. So just imagine, if I write cos phi over here plus 1, it will become 2 cos square phi by 2. So 1 plus cos phi will be 2 cos square phi by 2. So that is where this particular formula comes from. Yes, modern physics of 2024, you can use it for studying. Why not? You can use my Super 6 theories definitely even in 2025. It's not like it is invalid. I'm not like Hygen or some other scientists. Suddenly in 1 year the theory is invalid. You can use it. Okay. So if you want, you can write this 2 into 2 as 4. Root of 4 is 2. So it will become 2a, and root of cos square is just cos del phi by 2. So that is the resultant amplitude. Similarly, you can also find the resultant intensity, not a big deal. So the resultant intensity will be I1 plus I2 plus 2 root I1 I2 cos del phi, which is the phase difference. So I is basically common, and what I'm left with is 1 plus 2 cos del phi. Again, the same theory is applicable. It will just become I into basically 2 common and 1 plus cos del phi. 1 plus cos del phi, we just saw what it is. It is nothing but 2 cos square del phi by 2. 2 2s are 4, so it will become 4i cos square del phi divided by 2. So that is your resultant intensity in general when the two sources are identical in nature. This is very, very important. If they are identical, if they are not identical, then obviously they will not cancel out perfectly. This formula will not be applicable. This and this will be different. This I and this I will be different, and all of that. Is that okay? Everyone understood? This is only for two identical coherent sources. Two identical coherent sources what the amplitude and the intensity in resultant will look like. So I'll just block this off, and this is the most important word: two identical coherent sources. This also obviously are very important. As you can see, the maximum intensity will be 4I, whereas if you talk about the minimum intensity over here, that will be just 0. It will just cancel in the case of destructive interference. These formulas I have given you even in the previous lecture. This is just more like a recap or revision of this. Okay, cool, very good. Now what they do is, say for example, I have two sources over here, S1 and S2. There is a space around it, and I want to know where constructive happens, where destructive happens. So that is why I will choose some random point, let's say over here. I don't know whether it is going to be constructive, destructive, or neither of them. So I will think of it like this. Okay, the rays from source 1 will reach point P earlier. In this case, the rays from source 2 will reach it slightly later on. Let me join the two sources by some distance. Let's say over here, I will call it as D. Okay, I'm just going to call the distance between the two sources as D. And the location of the point, which is right over here, I will label it as R. And I will just show a perpendicular to S1 and S2, something like this. I will also mark an angular position of that point. I will call it theta. So what have I done over here? Just observe. S1 and S2 are two coherent sources separated by D distance, D, and you have taken a random point P at distance R, which is much larger than our D. If it is very small, it becomes difficult to analyze. So usually those distances, this point is very far from the sources, or you can think like this: the sources are here, this point is here. So this R is very large as compared to the distance between the sources. Okay, and has angular position given by theta. Angular position is given by theta. What I want to know, if both these sources generate waves, they won't reach the point P simultaneously. Obviously, this wave will reach first, this wave will reach a little bit later. If point P was here, then this will reach late, this will reach earlier. So there is a delay, there is a path difference which is created. So that path difference will help me understand constructive, destructive, and so much more. So if I want what is the path difference in general at that particular point, so I will write over here the path difference by the time the waves reach here. That delta x will be this path length minus this path length, so it will be S2p minus S1p. It will be nothing but S2p minus S1p. Everyone fine till this point? S2p minus S1p. Now, this is the very interesting part. Observe this. If this S2p distance if this S2P distance and this S1P distance, subtraction is delta x. If I want a constructive interference, then I will make sure it is n lambda for constructive, for bright regions. And if I want destructive interference, I will just ensure this delta x is odd times lambda by 2 for dark regions. That means my point P is somewhere, and I have taken two fixed points, and the difference of the distances, if it is, let's say, 5 lambda, then I know it is a constructive interference. If the difference of the distances is 7.5 lambda, because odd by 2 will be like 0.5, 0.5, 1.5, 2.5, 3.5, 7.5, 2.5, whatever. If it is something 0.5 lambda, I know it will be a dark region. Everybody with me? If it is just multiples of lambda, I know that point will have constructive. If it is something 0.5 lambda, I know it will be destructive in nature. Now, you know what? How I will get those points, or rather how those points will look like where constructive and destructive are? Well, that is a slightly complex mathematical analysis, but let me tell you how it looks. And that is the final result which you need to just keep in mind. Just observe this now. All those points where you will not see any kind of path difference will be here. If you stand anywhere on this line, this length and this length will be equal. So S2P minus S1P will be 0. So all these points will be of 0 lambda, my dear warriors. All these points will be basically of 0 lambda. So the path difference anywhere on these lines is just 0 times of lambda. You will see there are points like this. You will see there are points which go like this, where the path difference here is 1 lambda. Then you will also probably see points like this where path difference is 2 lambda, and so on and so forth. The same thing will also continue right over here. Yes, here also delta x is 1 lambda, delta x is 2 lambda. You can have more such things, more such lines. Actually, these curves that you see, they are actually something called as hyperbola. You have seen parabola, ellipse, circles. These are hyperbolas. They basically look something like this. Curved lines which do not complete diagram. They will just keep on extending till infinity like this. So they are called as hyperbolas. So you will see hyperbolas like this. If you are here, 100% you will see bright region or constructive interference or a maxima. Here, 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 all these are bright regions. But in between them you will see the destructive part, something like this. So here is where delta x will be 0.5 lambda. Here is where delta x will be 1.5 lambda. Here is where delta x will be 2.5 lambda. Here is where delta x will be, again 0.5 lambda. Delta x will be 1.5 lambda. Delta x will be 2.5 lambda. So these are the curves that you get, by which you can figure out by standing anywhere whether it will be constructive or destructive interference. That is how it looks like. Is it beautiful? Did you understand it, everyone? These are basically hyperbolas. What are they? Hyperbolas. Thank you, Madhumati, for reminding me. Now, just imagine somebody puts a screen over here. Somebody puts a screen over here. What do you think the person will see on the screen? What do you think the person will see on the screen? Come on, think logically, my dear warriors. That person will see a bright region, bright region, bright region, bright region, bright region, and in between that, destructive interference. Dark, 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 dark. So a person will see nothing but a fringe pattern, fringe or basically bands, band pattern on the screen, where each color over here represents, one is basically the bright region, bright band or the bright fringe, and the pink one over here represents the dark or the dark fringe or the dark band or the destructive zone over here. Yeah, so that is what you will see. The hyperbolas will intersect and you will see these lines cutting through that particular screen like this. Imagine hyperbola, tuck, 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 different places it is cutting. You will see these bands on the screen over here. But if somebody places the screen by chance over here, right? Imagine somebody places a screen like this over here. Somebody places a screen like this over here. Then it so happens that on that screen, you will, on that screen, on that screen, what you will see is basically something like this. You will see rings. You will see basically a ring pattern, alternate, alternate, bright, alternate bright and dark rings. You will not see fringes, you will not see bands. Bands is where you are placing it here, then these lines are cutting like this. But over here, understand these 2 points, axis, I can just draw, it's not just I can draw only this hyperbola. I can even draw a hyperbola like this. I can draw a hyperbola like this. So visualize this in 3D. So if you rotate that hyperbola like this, if you rotate that hyperbola like this around that axis S1, S2, you will see rings which are formed on the top screen. But over here on the front screen, when I rotate it like this, when it hits the screen, it will strike it, it will scratch it here. So it will make bands over here. So it will make rings on the top and it will make bands over here. So this is what happens. Okay, so this is something which you should be aware of. Now to see this particular fringe pattern, it's described over here. They use this setup called as the Young's double slit experiment, which is mentioned right over here. Okay, where you have basically you have two slits which are created and they will generate the interference pattern on a screen which is kept in a dark room. You need a dark room, otherwise you will not be able to see it very clearly because the interference patterns are usually very faint. But you generally do not take two light bulbs, rather you create a slit, two slits from a single light source. Why is that? Because whenever you take two light bulbs, no matter how good quality they are, no matter how nicely you make them, you will never be able to make them coherent, because there is always something which will ensure that they will not be in sync. Even if you manufacture it accurately, some atom here might be different from some atom over here, and they might not generate the waves together, so they will not be coherent. That is why you do not use two light bulbs, rather you take a single source or single light bulb and then let that light fall on two slits on a cardboard or a sheet or a opaque object. Because the two slits get illuminated from the same source, then they become coherent, and then that light falls on a screen which will create a fringe pattern. So keep this in mind. Independent sources of light, meaning two separate light bulbs, two different lamps, two different candles, they are always going to be incoherent. They will not be coherent in nature. But if you take derived sources, derived or dependent sources, what do I mean by derived? These two slits were dependent on this, they were derived from the original source. They will be always coherent in nature. This setup is then called as the Young's experiment, YDSE setup. Is that okay? This is basically then called as the Young's double slit experiment or YDSE setup. Now in this particular setup, the main thing that you need to know is that if you have these are the dark fringes and bright fringes alternatively. The distance between two bright or the distance between the two dark fringes, either of them, that is called as the fringe width. Fringe width beta, and that is given by lambda capital D by small d. Now what is lambda? Wavelength. What is small d? I already have told you this over here. It's the distance between the two sources. But the screen will be kept somewhere, right? So wherever the screen is kept from the sources, from the two sources, that distance is basically called capital D. Usually this d is much larger than the distance between the sources themselves. Is usually much larger than the distance between the sources themselves. Source to screen is usually very far. Sources themselves are very close. So that is capital D, and that is the first formula that you should be aware of. Okay, beta is basically lambda D by D. Okay, everyone? Perfecto? Understood? Clear? Next, the location where you will find the bright fringe. Let's say this is the central line. This is the central line. This is basically the central line on that screen. So from that central line, if you want to locate any, you want to locate the position, you want to locate where your bright fringe is. So the y coordinate of the bright fringe, that y coordinate of that bright fringe is just n times of beta, which means it is n times of lambda d by small d. You want to locate the second bright fringe, just put n as 2 times of beta. You want to locate the fourth bright fringe from the center, put n as 4, so 4 times lambda d by d. That's it. That's how you can locate any of the bright fringes location from the center. When I say center, I mean from here. So this was the center. So from the center, where is the bright fringe? So this was the center. From the center, first bright fringe, second bright fringe, like that. Is this clear? What do I mean by it? Okay. Lastly, if I want to locate any of the dark fringes, if I want to locate any of the dark fringes, then the y coordinate of those dark fringes is given by, right over here it is there, n plus half lambda d by 2. So n plus half times of beta, which is n plus half lambda capital D by small d. These are again two very important formulas. Okay, so keep all these things in mind. Location of the bright fringes and dark fringes, distance between the fringes, which is called as the fringe width, and obviously the formulas for your intensity, which was given right over here. Intensity, amplitude, maximum, minimum, etc. The shape of the fringes, all these things. All right. So that was your Young's double slit experiment. Let's come to now the last few parts, which is basically diffraction and polarization. So it will just take half an hour, Sukanya, and we'll be done with it. Yeah, just half an hour more. Okay. If you want, we'll take a 5-minute break and we'll quickly return. We'll just take a 5-minute break. No issues. This water break was enough. Welcome back, everyone. So let's continue with the last few parts, and one is diffraction and one is polarization. Now these are the next two important properties of light as a wave. So we saw interference, and the experiment related to that was called Young's double slit experiment. Now diffraction is again a kind of interference, but it involves just a single hole or a single slit, and when light enters a single slit or a hole, then you will see it will spread and it will create an interference pattern in itself. Not just that, even if light is passing and there is a edge or a corner, then light won't just continue going in a straight path, it will bend around that edge or that corner, and you will see it will go in different directions. And this is also true for sound waves. See, if somebody is talking in a room and there is a door, you need not have to stand in front of the door to hear them. Even if you are not exactly in front of the door, rather you are somewhere off, still the sound somehow manages to find a way and enter your ear. And this is a generic property of any wave, which is called as diffraction, which means the waves bend around the edges or corners, or when they are passing through holes or through slits. So this phenomena is called as diffraction. Sometimes it is good, sometimes. Am I audible now? Am I audible? Am I audible? Am I not audible? Hello? Just check, just check. Not audible, is it? It's showing audible over here. Guys, am I audible now? Just check, Madhumati. Is it fine? Audible? Okay, Suvanya. All right, cool, great. Okay. Sometimes this particular phenomena of diffraction happens naturally, and it is just then a phenomena, and you are explaining it like I just told you, light is passing through a corner and it is bending, or somebody is talking and you are hearing it. Sometimes it is undesirable, because imagine you are seeing through a camera or through a microscope or a telescope, then imagine the light coming from the distant star spreads, then the image will become blurred, not so clear. So that's when it becomes undesirable. It becomes undesirable. So that is basically diffraction. And then here we just have the formula for a single slit. We'll just come to that. But before that, let me show you how single slit diffraction exactly looks like, or just diffraction, how does it look like? Yeah. Okay, look at this. Can you see there is a single slit over here? This is one slit. Earlier, if imagine there was no slit at all, the light which is coming from that particular torch or that bulb or that source is just continuously going over here. But the moment I add two slits, we have seen they produce interference, and that was your Young's double slit experiment. That was your Young's double slit experiment, if you remember clearly. Yes, this was your Young's double slit experiment. Now instead of two slits, let's make it one slit. See how the light is spreading in all the directions. Can you see that? Yes, the light is spreading. If I change the width, the spread amount also changes. You can see that. If I change the width, you can see the amount by which the light spread also will change. And if I make the width very small, the spreading amount is again changing. So definitely light can bend when it passes through a hole or a corner, and it's not just true for water, even for light you can see this. I can just start this over here. Yeah, this is green light. I can make it blue light. Right now you can see this particular blue light is spreading by some amount. If I use a reddish light, it will spread by a different amount. If I use green light, it will spread by a very different amount. It also depends on how wide the slits are. If the slit width is changed, obviously the spreading also changes, and you will probably see some kind of interference happening over here. This not only happens with slits, it also happens with holes, which are also apertures, which are in the cameras or telescopes or microscope. See, there is a hole over here, and I will see this sheet is there is a hole here, and there is a screen here. So when the light from this torch passes through this hole, a small dot is there. I don't think you will be able to see it in your computer screen. I can see it here. There will be a interference which will be formed over here. Just see this. Observe. The light went through this hole. Most of the light got blocked, but the light spread. But when it spread, it did not spread evenly. There was an interference pattern. You can see alternate bright and dark rings which are formed over here. Alternate bright and dark rings which are formed over here. If I change the diameter of the hole, if I make the hole bigger, you can see the interference pattern has changed. If I make the hole thin, very narrow, the interference pattern has changed. I can also use different kind of holes, and I can see different kinds of diffraction patterns. Look at this, how different diffraction patterns are observed. If there is a cutout of a figure like this, see how that cutout is looking over here. Whereas if I make the hole small, it is looking like this. So different patterns can be observed because the light is spreading and it is creating some kind of interference pattern. Is this clear? What is this diffraction? So diffraction, you might be wondering what exactly it is. I'll tell you what. When the light is passing through this hole, no? When the light is passing through this hole, each point on this hole behaves like a source, and imagine there are infinite such sources in this hole. In Young's double slit experiment, you had two sources, two slits interfering. Imagine not two, but 100, 200, 500 sources here, and all these sources are meeting together. That creates that interference. So actually, diffraction is interference of many sources within that hole or within that slit. Same thing you can observe for this single slit diffraction over here. When I use light and single slit over here and I turn it on, think like this. In this slit, 1, 2, 3, 4, 5, 6, some 700, 800 sources are there. Just imagine. Just imagine. Each source will interfere with all the other sources' waves, and that produces the interference pattern. So diffraction is interference of multiple sources within that slit or that hole or that aperture, and that is what you will see. Even on the next slide, they have mentioned that over here. There has been a discussion about what is the difference between interference and diffraction. And then Richard Feynman, who is a very famous physicist who also won Nobel Prize, in electrodynamics in 1900s, he says no one has been ever able to define the difference between interference and diffraction satisfactorily. It is just a question of usage, and there is no specific important physical difference between them. The best we can say is roughly speaking, when there are only a few sources, say two interfering sources, then the result is usually called interference. But if there are many sources, the word diffraction is what you use. Because if there are many sources, thousands of them, then the pattern produced is basically then called as a diffraction. Okay. In Young's double slit experiment, notice one important thing. Remember the Young's double slit experiment. Actually speaking, this and this is interfering, but at the same time, this slit is also creating a diffraction. This slit is also creating a diffraction. So there is diffraction diffraction and these two together interfering on the particular screen. So it's a combination of diffraction and interference on the main screen. So it is not a just simple interference, it is a superposition. So very important line over here. In the double slit experiment, we must note that the pattern on the screen is a superposition of the single slit diffraction from the slits or the holes and also double slit interference pattern. It's a combination of both of them. You can also see these diffractions, whatever I have shown over here, whatever this particular diffraction that you are seeing, you can see this diffraction. You get a small slit, right? How do you create a small slit? Take two shaving blades and place them close to each other so that there is a small gap and let a light beam pass through those slits like it has been shown over here. Take through shaving blades, keep a small gap and let light pass through it. If you are in a dark room and you see a colored light, on the other side you will see a nice pattern which is formed on the wall. So that is again a diffraction pattern. Is that okay, my dear students? Did you understand what diffraction is and what's the difference between diffraction and interference? Interference is when you have two or three sources meeting each other. Diffraction is when you have many thousands of sources meeting together. So in a single slit, there are many point sources which meet and create that interference. But that word interference, which you traditionally use in Young's double slit experiment setup, is where you have two sources, two or three sources meeting together, very few amount of sources. I hope this is understood. Now there is a formula for, a single slit interference. You will see bright, dark alternatively formed. Yeah, just like over here, a single slit is there. On the screen over here, you will see alternate bright, dark fringes which are formed. So the location, imagine this is the screen. So this is the slit. The slit's width is A. The width of the slit is basically given to be A, as you can see over here. That light will come over here and fall. So if you are looking at any point on the screen, it makes an angular position theta. Then if you want maxima, basically bright region on the screen, the condition for that is n plus half into lambda, which is the wavelength, by the slit width, is equal to the sine theta, whereas if you want a minima or basically a dark region, then the condition for that is n lambda by A is basically the sine of theta. Okay, now because theta is usually small, sine theta can be approximately taken as tan theta, can be approximately taken as theta as well. So these approximations are valid only because theta usually is very small. So theta is very small usually. That's when you use this approximation. Otherwise, you just keep it as sine theta, then it is equal to, else for small angles, then we will use approximately theta or tan theta, small angle approximation. Very good. So that is what has been mentioned over here. Please note this formula is exactly opposite of Young's double slit experiment. Yes, in Young's double slit experiment, for minima it was n lambda, sorry, for minima it was n plus half lambda by a, and for maxima it was n lambda. So just observe this, exactly opposite. Where did it go? Yeah, the y coordinate. For maxima it was n times some lambda d by t for maxima. For minima it was n plus half. Here for minima it is n plus half, but in case of diffraction, for minima it is n and for maxima it is n plus half. Exactly opposite formulas. That is slightly confusing. If you know one, you will automatically remember the other. Just remember it is opposite. If you forget that it is opposite, then gone. If you use the same kind of formulas, then you will get a completely wrong answer. All right, that's something which you should be aware of. Okay, now let's come to polarization. This is another interesting phenomena. I will explain. Now, basically, light is, we know, a transverse wave. Meaning, just forget this orange part. We know, there is something which goes up and down, and that is electric field, and something which goes again left and right, that is the magnetic field. So light is a transverse wave, meaning whichever direction light travels, there is something which goes perpendicular to the direction in which light goes. So if the light goes like this, something goes, and that something being the electric field or the magnetic field. So we know light is a transverse wave. So initial part, they have just defined what a transverse wave is, and transverse wave is where, they have just mentioned the displacement is along the perpendicular direction to the propagation of the wave. Such a wave is basically called as a transverse wave. Since the displacement is in y direction, often it is called, now this is important, it is called as a y polarized wave. Since each point on the string moves in a straight line, the wave is also referred to as linearly polarized wave. Further, if the string always remains confined to the xy plane, it is also referred to as plane polarized wave. What do I mean by that? See, if just for the sake of understanding, imagine this was a string. This string is having a wave which is going on it. That means each point on the string goes up and down, up and down, up and down, up and down like this. Imagine this was the y-axis. If the points on the string go along the y-axis continuously, and even after 1 hour or 2 hours or 5 minutes, I see they always go up and down along the y-axis. Never they go along the z or some weird direction. Then the wave is said to be a polarized wave. Polarized means it is made to behave in such a way, that it will always stick to its agenda. It has been polarized now, and it will stick to its y-axis. It is now going along a line which is the y-axis. So I will call it as a line polarized wave. But it's not just one point. Actually, all the points on the string go up and down, up and down, up and down. This is the y-axis. This was the x-axis. So this is the xy plane. So all the points, whenever you look, are always in that plane. So just imagine you have a wave which is always in a plane like this. You never see a point which is going out of that plane. Such a wave, it could be any plane. It could be a plane like this. It could be a plane like this, doesn't matter. Such a wave is basically called as a plane. There is a plane over here, plane polarized wave. It is called as a plane polarized wave. Did you understand what is the meaning of a polarized wave? A wave which is confined to oscillate in a peculiar direction. It could be any direction, and it is such that all the points are in that same plane, and no matter when you see it, such a wave is called as a plane polarized wave. No, see, Tejas book will help you practice NCERT questions. For 680 plus, you need to practice with PYQs also, Tanuja. Not just NCERT, but you also need to practice PYQs. Okay. Now comes the next part. How do you show? Oh, is there something called as unpolarized wave? The answer for that is yes. Over here, as you can see. If the plane of vibration is changing randomly, then what we have is something called as an unpolarized wave. So for an unpolarized wave, the displacement will be randomly changing with time, though it will always be perpendicular to the direction of propagation. So just imagine this. Sometimes the particles are going like this, sometimes like this, sometimes like that, sometimes here. So it is randomly changing, but no matter what, see, if the wave is going here, it's always going perpendicular. It's always going perpendicular to the wave. So it is a transverse wave, but the direction of oscillation is continuously changing. So it is no longer a polarized wave. How do you show whether a wave is polarized or not? Say for example, a wave is coming towards you like this. The oscillations of that particles are like this. Then I would say, if I show the wave in this particular manner, I would say it is a plane polarized wave. But imagine the wave is coming towards you, but sometimes the particles oscillate like this, sometimes the particles oscillate like this, sometimes they oscillate like this, sometimes they oscillate like this randomly. Then it is unpolarized wave. 100%. It is not polarized. As the wave come towards you, sometimes they are going like this, like this, like this. So it is not polarized at all. There is one more type of wave which is unpolarized in nature, but in a very peculiar manner. This is called circular unpolarized wave. Meaning, what happens is, see, these vibrations are not constant in all the directions, but imagine in all the directions the vibrations were constant. In all the directions, the vibrations were constant. So in that case, you will see a nice circle being formed. So that's why it is called as circular unpolarized wave. It is still unpolarized, but it is a circular unpolarized wave. This is just randomly, this is just a random unpolarized wave. This is a properly polarized wave. So this is polarized. These two are not polarized. They are unpolarized waves. Did you understand the difference between them? Very good. Now, what happens when such a polarized wave enters a peculiar crystal or an organic compound or a peculiar medium or a apparatus which can only allow vibrations or oscillations in a particular direction? Such mediums or crystals or organic compounds or apparatus which only allow vibrations in a peculiar direction to be passed through, they are called as polaroids or polarizers. Well, here it is given. Polaroids. A polaroid consists of some chain of molecules, blah blah blah, that is not important. The electric vectors only in a peculiar direction which are aligned to the molecules get absorbed. So if an unpolarized light is incident, then the light wave which is polarized in a peculiar direction only gets passed and other gets absorbed. This is known as the pass axis of the polaroid. Let's understand this. These polaroids, these compounds, these crystals, they have some long chains of molecules. What do these chains of molecules do? In a light, you have electric field wave and a magnetic field wave. Let's focus on the electric field wave. This electric wave, which is along the direction of the molecules of that crystals or that compound, okay, they get absorbed. So those molecules of the crystal, if they are in this direction, then all the electric fields in that direction, they will get absorbed. So naturally the other electric field, if present in any other direction, they will be allowed. Then the light wave, if it is unpolarized, meaning once it is oscillating like this, once here, only a certain component gets absorbed by the long chains. Certain components is just allowed to pass. Now, the the direction which allows the electric field to travel, to pass through without getting absorbed, that is called as the pass axis of that particular Polaroid. So let's see this through this particular demonstration. Do you see this particular light over here? Can you see one oscillation is here, one oscillation is here, one oscillation is like this? It's all random. Can you see that? But the moment it passes through this particular apparatus, it has a pass axis. It passes, allows only vibrations which are in this direction. Anything else, it will block it because it is opaque. So imagine that organic compound or those crystals also to behave in a similar way. Only those vibrations in this direction are allowed. Any other direction are not allowed. So an unpolarized light becomes polarized when it passes through something called as a polarizer. Got it? When it passes through something called as a polarizer, this is the pass axis. This is the pass axis. Imagine somebody places one more identical Polaroid in front of it. Coincidentally, the pass axis exactly aligns with this. So then there is no problem at all because the vibrations are already in the same direction as the pass axis. So the entire wave will pass through. The entire wave will pass through without any problem because the pass axis will allow those vibrations to travel. But just imagine if I turn this, only a component of that wave will be allowed to pass. Can you see how this particular wave turned? Only a component of that wave will pass. And just imagine I make it perpendicular, then nothing will pass because all the vibrations are in the y direction. There is nothing in the z direction. So nothing will pass. So if I take two Polaroids in perpendicular direction, no matter which light you use, unpolarized, polarized, God knows what, 100% complete light will get blocked. 100% complete light will get blocked because the first polarizer will ensure only a component will pass. The next polarizer, being perpendicular, will not even allow that component. But if I choose any other angle, then a small component of it will pass. I can have multiple Polaroids like this, let's say for example this way and then like this. So I can keep passing a component of this Polaroid into other Polaroid and so on and so forth. I can have multiple Polaroids arrangements like this and each can pass a component of each one to the next one. So this is how Polaroids and polarizers work. Is this absolutely clear, my dear students? What is the meaning of a polarizer? Polarized wave, Polaroids. Everybody clear? Okay. Now the following laws are there. I will just show you over here. If you have unpolarized light, and that passes through a Polaroid whose pass axis is like this, then on the other side you will get light which can oscillate only like this. If this had an intensity of I, this will have intensity of I by 2. This is the first property rule that you should know. Exactly half of the light will enter in, half of the light will be cancelled out. The next rule that you should know, oh by the way, this has now become polarized. This has now become polarized. If you already have a polarized light, but you pass it through a Polaroid whose pass axis is at an angle, the pass axis is making an angle. The pass axis itself is making an angle with the plane of polarization of that particular wave. The light which will come out will be along that pass axis, but it won't be having the same intensity. Rather, if the intensity is I, then this guy's intensity will be I cos square theta. These laws are basically called as Maloo's law. Maloo's law. So very important. If unpolarized light is there, it will become I by 2 after the polarizer. If it is already polarized, then depending on the angle, the intensity will be I cos square theta. That is called as the Maloo's law. As you can see over here, it is clearly mentioned. I cos square theta. This is called as the Maloo's law. Okay. Polarides can be used to control the intensity of sunglasses, windows, etc. So you might have seen these windows which look very transparent, but somehow they do not allow any light to enter inside the room. So actually they are made of those special crystals and compounds with long molecular chains inside that glass, and they might look transparent, but they will block a lot of sunlight. So maybe there is a film here and a film there, and controlling the angles of the film, you can choose how much light will enter and how much light will not enter. Okay, so these are basically some of the applications of Polaroids. They are also used in movie cameras, 3D movie cameras, also in sunglasses. When you wear those Polaroid sunglasses, that is controlling how much light is going to fall onto your eyes and preventing any damage to your eyes. So all these things are some of the applications. Let's have a look. Look at this example. Example 10.2. Discuss the intensity of the transmitted light when a Polaroid sheet is rotated between two crossed Polaroids. Okay. Now, two crossed Polaroids means there are already two Polaroids made in such a way that they are perpendicular to each other. So, imagine there is a Polaroid 1 over here. There might be unpolarized light which is falling onto it, but after passing through P1, it will have vibrations only in one direction, and let that particular intensity just once again. And let that particular intensity be I naught. Okay, so actually there are two polarites, but let's just say some unpolarized light was there. Maybe the intensity was 2 I0, and then after passing through the first Polaroid, the intensity just became I0. Now, before that second Polaroid, there is one more Polaroid. Okay, and this particular Polaroid, I am allowed to change the angle. I am allowed to change the angle like this. Theta. I am changing the angle. So what will happen to the light which will come out of this? The light which will come out of this will have an intensity of I0 cos square theta. This light then further falls on the next Polaroid whose path axis is perpendicular. Remember, two crossed Polaroids. Crossed means perpendicular. So this Polaroid P2 is perpendicular to P1. So when this light falls onto this, the final light will be in this peculiar direction. For that, I need to know what exactly is this angle. Well, if this is theta, this is 90, obviously this will be 90 minus theta. So the intensity of the light that you will be getting over here will be I0 cos square theta will be the incident intensity. That guys cos square 90 minus theta. The incident light intensity is this, using Maloo's law, multiplied by cos square angle between the polarization and the path axis, which is 90 minus theta. That is the catch in this problem. Cos 90 minus theta is nothing but sine theta. So this will be cos square theta into basically sine square theta. So that is what they have done. Cos 90 minus theta is sine theta. So it is I0 cos square theta into sine square theta. So that is the final answer. But if you want, you can also write it in different forms like they have done over here. As you can see, I can just write it as I0 into 2 cos theta sine theta, the whole square, but 2 was not there. In fact, 2 square was not there, so it will be 1 by 4. So it will become I0 by 4, and this will become sine 2 theta, which means the intensity of the light will change with this function. So basically you had two perpendicular Polaroids. In between them you added this another Polaroid and you kept on changing the angle. This Polaroid made theta with this, but with the next one it will make 90 minus theta. So first intensity, if it was I0, next will be I0 cos square theta, next will be I0 cos square theta's cos square 90 minus theta. Maloo's law 2 times you apply and use simple trigonometry, you will get this as the answer. Got it, everyone? Awesome, awesome. So this is another interesting application of Maloo's law, how you can control how much light will come over here by controlling this Polaroid. I can adjust this Polaroid and you will see I will be able to control how much light will come out of this second Polaroid. It's a beautiful application. All right. So I think that was the last part of it. Yes. So I want everyone to put in the comment section wave has been opted, wave opted in the comment section if you have watched this. So this was the last part of your NCERT line by line, and I'll be seeing you with more further announcements in the days to come, and I will keep you updated on how NEET Express is going to progress in the form of questions and PYQs as well. Okay, so I hope you guys enjoyed. Hi Nandu, good afternoon. Thank you Madhumati, glad you guys enjoying the class. Thank you Warrior Pandus. Thank you Evening Star, Mardai, Sukanya, wave opted. Very good, very good. Keep it up. So obviously a lot of questions practice is needed. Theory has been done. Now you cannot complain that sir we do not have theory on the channel, sir we don't have theory on the platform. Everything has been provided. No more excuses. Questions practice is what you need. That also we will do. Okay, take care. Have a great time. Bye bye.